So you've probably watched a demo of a modern AI agent recently and just thought, wow, it's completely seamless, right? You speak to it, it sees your camera feed, it hears the exact tone of your voice, and it immediately talks right back to you in real time. Honestly, it feels like magic. But behind that magic is some of the most intense, mind-bending engineering happening on the planet today. Today's mission for this explainer is to completely demystify that magic. We're going to look under the hood of what we call any-to-any AI, specifically focusing on an open ecosystem model known as MIO to understand exactly how we build models that can see, hear, and speak all at the exact same time.
Okay, let's dive right into this. Think of this as a thrilling anatomy lesson mapping the AI from its senses all the way to its education. We'll be looking at the real-time problem, 4 senses, 1 vocabulary, the need for speed, the 4-stage curriculum, chain of visual thought, and finally, the open frontier.
All right, part 1, the real-time problem, or as I like to think of it, escaping the telephone game.
To really appreciate where we are right now, we have to understand the massive hurdle that earlier AI architectures kept tripping over. Until very recently, getting an AI to act multimodally was this clunky, hop-by-hop pipeline process. You'd have a vision model that looked at an image, turned it into text, passed that text to a language model which generated a text response, which then went to a text-to-speech model. Every single hop acted like a bad game of telephone. You're losing information, you're adding massive latency, and it becomes an absolute nightmare to train. The breakthrough target that models like GPT-4o and the open-source MIO achieve is the any-to-any architecture. It relies on a single, unified causal transformer. That means it's one cohesive neural network, predicting what comes next in a straightforward sequence. One brain, compressing data just enough to be essentially lossless and delivering a sub-second response. It's a total game changer.
Moving on to part 2, 4 senses, 1 vocabulary, building the universal dictionary.
So how do you actually give one digital brain all of these different senses? Well, you have to solve a huge engineering puzzle, compressing text, image, speech, and music into a single shared language of numbers. You create a shared vocabulary. Think of it as a universal dictionary totaling roughly 48,000 tokens. And this brilliantly illustrates how the model strictly allocates disjoint ranges of IDs for each sense. Text gets the lion's share, around 32,000 standard text tokens, which are your usual word fragments. Music gets about 8,000. Images get 4,000 using compressed visual codes, and speech gets another 4,000. By rigidly dividing this space up, the AI completely prevents collisions. There's no way it confuses a word for a pixel or a pixel for a sound wave. They all just become native numbers that the transformer can easily digest.
Actually, what's really fascinating here is how we squeeze something as wildly complex as an audio waveform into those simple integer tokens. We use a technique called residual-VQ, or vector quantization. Imagine a 16 kHz audio wave. Residual-VQ chops that up and encodes it into 8 hierarchical codebooks. Think of it like building a cake. The base layer, layer 0, acts as the foundation. It captures the coarse content, literally the actual words being said. But then, the subsequent layers stack right on top of it, adding all the rich human details, the prosody, the emotion, the specific identity of the speaker. This is what gives the AI a sense of hearing and a rich voice, without completely breaking the transformer's token limit.
Right, on to part 3, the need for speed. Let's talk about reflexes and latency budgets.
Okay, so we have our senses, but now we have to make them reflex fast. When you're having a natural conversation, milliseconds absolutely matter. 300 milliseconds. I really want you to anchor on this number. This is the incredibly tight baseline latency budget for a model like MIO. If it takes longer than 1/3 of a second to reply, the magic is instantly broken, and you just feel like you're talking to a clunky machine on a severe delay. By the way, some experimental designs are pushing this even further. There's a model out there called Mohushi that claims an astonishing 160 millisecond round-trip latency. It's mind-blowing. To get a bit more technical, the crucial metric here is TTFAB, or time to first audio byte. What does that actually mean? Well, it's the exact latency measured from the split second you finish speaking into your microphone to the precise instant the AI spits out its very first audio output token. For an AI to feel natural and conversational, this absolutely must be kept under 500 milliseconds. Anything above that half-second mark, human users just start accidentally talking over the AI. It dictates the entire feel of the interaction. Let's walk through exactly where that time goes. Getting your voice from the mic into those audio tokens, that burns about 50 milliseconds. The model pre-filling those tokens along with the conversation history, about 100 milliseconds for an 8 billion parameter model. Generating the very first output token, another 50 milliseconds. And finally, decoding those output tokens back into audio you can hear takes about 100 to 150 milliseconds. To hit these lightning-fast numbers, engineers rely on a secret weapon, parallel decoding. While the transformer predicts the base speech tokens, a parallel residual quantizer is simultaneously predicting the emotion and prosody layers. If they tried to do this sequentially, hop by hop, it would just be way too slow.
So that's the physical architecture. But what about part 4, the 4-stage curriculum? How do we actually educate the model?
How do we train a model to use all these senses simultaneously without just scrambling its brain? We put it through a very strict, logical 4-stage school. Step 1 is alignment. We feed it massive amounts of paired data, text with an image, text with speech. This builds up that 48,000 tokens shared vocabulary we talked about. Step 2 is interleaved. We give it complex documents. Think of a blog post that contains text, images, and embedded videos all mixed up together. Step 3 is speech enhanced, where we pour in extra audio data to really lift the voice quality. And step 4 is SFT, or supervised fine-tuning, teaching it to actually follow instructions across all these modalities. Now listen, here's the absolutely critical part. You cannot skip a step. If you skip step 2, the interleaved stage, the model will fatally lose its cross-modality context. It won't understand how a picture relates to the paragraph of text right next to it.
Next up, part 5, chain of visual thought, the internal scratchpad.
Okay, this is honestly one of the most mind-bending concepts we're going to cover in this whole explainer. How a model like MIO handles spatial reasoning. Imagine you ask the AI, is the cat climbing a tree? A purely text-based model might really struggle to spatially map out that image. So MIO uses a visual scratchpad. Step 1, before it even answers you, it literally emits image tokens to sketch out the scene internally. Step 2, it emits text analyzing its own internal sketch. And finally, step 3, it emits the final spoken or text answer to you. It is quite literally drawing itself a picture to help it think through a spatial problem before it opens its mouth. It's wild, and it dramatically improves performance on complex visual benchmarks.
Finally, part 6, the open frontier. Let's look at the competitors and the limitations we're still facing.
We've seen the magic, but what does the broader open source landscape actually look like out there? Well, MIO definitely isn't alone. A quick survey of the competitors shows a really vibrant ecosystem. You've got AnyGPT, which is essentially the conceptual ancestor to MIO, handling 4 modalities. There's Unified IO2, adding vision action outputs like depth and normals, though on a smaller scale. You've got NextGPT, which hooks an LLM up to modality-specific diffusion decoders, and CoMIO, which relies on composable diffusion. But among all these peers, MIO really stands out as the closest thing we have to a pure token any-to-any generation machine.
But, and this is a massive but, building any-to-any models stays incredibly hard. Despite this brilliant single transformer architecture, OpenAI still stumbles. For one, speech quality still trails behind the closed proprietary models. Remember that residual-VQ tokenizer? Well, it compresses audio heavily, which means it's inherently lossy. Because of that, open models often still sound just a tiny bit robotic compared to the best human-like synthesizers out there. Second, cross-modality reasoning frequently fails on complex prompts. If you hold up a picture to the camera and say, "Hey, sing a song about what you see," the model will probably struggle. Perfectly blending vision, text reasoning, and musical audio generation, that is still very much an unsolved open research problem.
Which leaves us with this final, really profound question to think about. As we keep scaling these incredible any-to-any models up, can an OpenAI ever truly sound perfectly human? Or, because we are literally forcing sound and vision into discrete, compressed, lossy integer tokens just to satisfy a transformer, are we forever bound by fundamental technical limits? It's this ultimate tension between massive, breathtaking scale and harsh engineering constraints. I really hope this explainer helped demystify the magic for you today and leaves you hungry to keep an eye on this incredible frontier.